And today, I want to introduce a paper about semantic segmentation. This paper was published in ICCV 2021, and the title is Integrate Image Level and Semantic Level Context for Semantic Segmentation. And I will introduce this paper from the following contents. First, I will show you some background information about the semantic segmentation and the context aggregation. Next, I will introduce the proposed method, and I will introduce from the overview and image level context module and the semantic level context module. Next, I will show you some experiment results. Finally, we will land on the conclusion. Now, let me give you some background information about semantic segmentation. I think we have already familiar with this task. The semantic segmentation in this task, when given an image, we want to generate pixel-wide semantic predictions. And we can see that there is an example. The input is a cat in a picture, and the output, we want to assign a category label for every pixel. That is the semantic segmentation. And the recent studies mainly focus on two issues to further boost the semantic segmentation performance. So one is that how to improve the encoder structure so that the model can extract more robust representation for every pixel. And here is an example. This network tried to construct a dedicated structure to get a robust representation for the input. And the second one is the author tries to introduce richer contextual information into the original feature representations. For example, we can adopt different sets of convolutional kernels or use the feature pyramids to get the multi-scale feature maps. And here is an example, the feature pyramids. And the second one is also the interest of this paper. When talking about the context aggregation-based semantic segmentation, it has raised wide interest because the wide field of the view is very crucial for this task, and it has been studied in many research. The famous one is DeepLab. It utilizes Ultra's convolution kernels to force the network to perceive larger area and obtain the higher resolution output. The second famous is ISNet. It adopts spatial pooling to gain the feature maps of different receptive field sites so that the combined feature maps could aggregate multi-scale object clues. However, even though the current method has achieved impressive results, these solutions only focus on aggregating the contextual information from the perspective of the whole image. That is the image level contextual information. And in the meantime, they maybe discard the significance of the pixel representation of the same category. And they all suffer from the same issue that the contextual information of each pixel is unevenly captured from the true area and the regions of other categories. Here is an example. This is the input image, and the middle one is the segmentation ground truth. And the right one is the segmentation result of a method which just considering about the image level contextual information. We can see that for the small scale object, for example, this animal, maybe we will give them a wrong label because we just consider about the image level information and ignore the figuring details. So to overcome this problem, in this paper, the author proposed to augment the pixel representations by aggregating the image level and semantic level contextual information respectively. And the main principle has showed in this figure. We can see that there is a semantic level context for car. This is the contribution of this paper. And they also use the image level context for the object. And then the author used the semantic level context and the image level context to augment the pixel representations of the car. And finally, they will get the high performance results. Next, we will come to the overall. And because in this paper, there are too many formulations, so make it clear, I annotate the formulations with the overall flow.
Jessica,
and, yeah.
Just missed about the image versus semantic level, the difference. Could you just repeat that?
Okay.
The image level versus that of semantic, what's the difference?
The semantic level means we just consider about the pixels which belongs to one category. For example, in this input, we know that this part, this region is car. And the semantic level contextual means we just consider about the contextual information in this area. However, in the image level context, we consider the contextual information in the whole image. And this is the difference between the semantic level and the image level.
It's still not clear to me what the difference is. So for the semantic level, you're saying that the car, for example, there's an outline, and obviously pixel level of semantic representation for the cars, which obviously is all the blue pixels there. But for the image level, right? Image level context for car, you just have some
other categories,
some purplish color there. What does that mean? Is it like the overall background?
The purple, the image level context means we consider all the categories in the image. We extract the representations from the whole image. However, the semantic level, the semantic level means we just calculate the contextual information in the car.
Right. And the image level means all other elements outside of the car, the background?
No. Image level means we take them equally. We treat every pixel equally when we calculate, when we send the image to the network and get the representations. We treat them equally. However, in the semantic level,
it's for your information, it's not that obvious. So I think maybe if you could show some other figures to explain what you meant by the difference between the two, semantic level versus that of the image level. I'm still very much confused. Do you have any other example?
Maybe this can be an example. We can see that it is the basic segmentation structure, and it is fully convolutional networks. We send the input to the network, and we don't give any weight to some regions. For example, the cat, we just send the whole image to the network, and finally we will get the output segmentation results. However, in the semantic level, we want to give more importance for the cat region. So we will construct a semantic level contextual module and put some weight on the cat region, that is the semantic level context.
Okay, what about image level?
Image level, that is we send the whole image to the network, and the network will learn the information from the whole image, and he treat every pixel equally.
Oh, okay. So you're saying, if I can understand correctly, the semantic level is to assign certain weights, whereas for the image level, you're saying that all pixels are equally weighted.
Yeah.
Is that what you're saying?
Yes.
In other words, you're not assigning any special weight on any of the components or segments.
Yeah,
of the
exactly.
Okay, all right. Let's go back to slide 7.
Yeah.
Okay, so that's what you meant, right? Okay, so on the top semantic level, you're saying you're assigning special weight to make it differentiated away from other background. Whereas you're saying that at the image level, there's no special weight assigned.
Yeah, exactly.
Okay, all right, thank you.
Thank you. Let's continue about the overall formulation. First, we send the input to the backbone. We can take the ISNet as a backbone. It is an example. And then we will project the pixel in the image to a nonlinear embedding space so that we can get the representation R. And the SLCM represents the semantic level context module. It is designed by the author, and the ALCM represents the image level context module. I will introduce these two modules later. And now we just focus on the flow. And there are total 2 branches in the overall structure. For the first branch is about semantic level. We can see that after sending the representation R to the semantic level context module, we will get the representation RSL. The RSL has been encoded with the semantic level information, and then we will calculate the similarities SSL between the representation R and RSL. We will get the similarities. Then we will use the similarities to encode the RSL and get the representations R prime. And similarly, for the second branch, it is used to calculate the image level context information. And we send the representation R to the image level context module and get the RIL, which included with the image level information, context information. And same, we will calculate the similarities SIL between the representation R and the RIL. And we will use the SIL to encode the representation RIL. And now we will get a total 3 representations R prime ST and R prime IL. The first one represents the semantic level encoded representation, and this represents the image level encoded feature map, and the original feature map from this part we will do the concatenation operation on these 3 feature maps, and we will get finally auxiliary representation, which will be used to calculate the loss function later. And the box with the blue boundary represents the shape of the tensor. And this is the overall formulation of this paper. And now next I will introduce the semantic level context module and the image level context module respectively. And for the image level context module, it is designed to capture the contextual information from the respective of the whole image. We can see that this part actually corresponds to here LCM. And first, we will calculate a matrix which storing the global context information of the corresponding channels. So this one is the channel-wise mean value. And then we will use it to add it to the pixel representations to obtain the RNL. And repeat. We do the repeat operation to make this one has the same size of the representation R. And then we will get the representations which has been encoded with the image level contextual information. This is a very simple image level contextual module. And the author said this module can be replaced by any other modules, for example, the ISPP, and it is very universal image level module. And
can you go back?
Yeah.
The second line, G.
Yeah.
Okay, so you have on the denominator H and W. Where do they come from?
H represents the height of the input, and W represents the width of the input. And we can see that back from the overall flow, we input the image to the backbone, and we will get the representation R with this size. C represents the channel, and the size of the feature maps is this. So let's come back to this. The R has the size of this one. Yes, it is the shape of the feature maps feature representation.
Okay, hang on a second. So R sub star I and J. So R I and J, what does that? What do those indices represent? R comes from your ResNet output, right?
Yeah.
So ResNet builds this tensor R of a representation.
Yeah.
So what is the, is that a star or R sub star RJ, IJ? Do I see it right?
Yeah.
So where do those indices come from?
I and J represent the indexed element of a matrix.
So you're talking about the spatial, right? I and J is the spatial feature index.
Yeah,
and star
exactly.
then represents the channel, or obviously is a three-dimensional tensor, right?
In this paper, the author said the star represents maybe the elements of a matrix. He didn't mention.
Could you repeat that again? I didn't follow what you said.
As far as I understand, I think the star represents the elements of a matrix. The IJ represents
elements of the matrix.
spatial elements.
Okay, so however this is summing of your representation, and in the end, you're really turning into a one-dimensional, right? It says matrix of size C top by 1 by 1.
Yeah.
So it means it just becomes one-dimensional. Is that what it is saying?
We already know that the R have C channels, and now the G is the channel-wise mean values of representation R. So the G has a set of C
okay,
plus
so
1
it's
plus
a
1.
it's a mean value for each channel.
Yeah, exactly.
And so okay, and so you get that G that basically then multiplies to or you concatenate with R. Is that what it is? Or add it into each of the pixels?
The F represent it is realized by a one by one convolutional layer. And the author says the F is a transform function used to fields G and R.
Okay, F so G is added into pixel representation R to obtain R sub IL, right? And then you said that's F of a repeat G. So
yeah.
What does it mean by repeat of G? What does that involve?
Repeat is used to repeat the elements in the corresponding channels of G to make G have the same shape of R.
Okay, so in other words, you're basically adding these mean values to representation R. Is that what it is? Of each elements?
Sorry, I didn't follow you.
So what you're saying, you're basically adding the mean values you got from G, right? G is basically a mean values by the number of channels you have.
Yeah.
That's what you said.
Yeah.
And so for each channel, you're just adding this mean value to every element of R?
This represents it is the concatenation operation.
So if it is concatenation,
yeah, this symbol represents
okay. So then you're just in that case, if it is concatenated, you have same number of channel as R, right? G has same number of channels as R.
So we need to do the repeat to make the
And
G
so
have the same size with R.
You are having the same spatial dimensions as R, right? That's what you are trying to do here? Repeat G? Is that what it is?
Yeah.
So you're having the same spatial dimensions as R and then same channel numbers.
Yeah.
And so your channel is doubled here then when you concatenate.
Yeah.
Okay. And so that's what the operation within the parentheses is, right?
Yeah.
And then what does F stand for? What does F do?
F is achieved by a one by one convolutional layer. And let's go back. RAL here. It is used to reduce the channel because we want to get a channel, want to get the RIL, which has the same shape and channel with the representation R. However, if we don't do the one by one convolution, there will be double channel of the output.
Okay, so you're just reducing the number of channels by one convolution here.
I think, yes.
So by doing so, you're essentially in the end kind of adding the stuff, right?
Yes.
Okay, all right. And so you compute this R sub IL, which in a way, is sort of like adding some mean values to the representations in the end. Isn't that so?
Yeah. Image level context information.
But this is, adding it per the channel, right?
Yeah.
Each channel has different mean values. So you're really adding these values to all these different channels and just elevating the values.
Yeah.
And okay, so all right. So it's equally applied to the entire spatial domain dimension. That's what they're trying to do here as an image level.
Yeah. Exactly.
Oh, okay. All right. You can go on. Thank you.
Okay. Thank you. After knowing about the image level context module, let's come to the semantic level context module. And it corresponds to this part in the whole architecture. And semantic level context module is proposed to aggregate the contextual information within individual category regions. And first, the author introduced a classification head to predict the category probability distribution D of the representation R. And according to the distribution D, the representation R can be grouped into various category regions. And similarly, we can do the same operation for the distribution, and we will get RCK and DCK. Next, we will aggregate the semantic level contextual information for each pixel representation according to their category. And we calculate the region representation for each class. We will get R prime CK. And
hang on a second. I'm trying to catch up here. So on the second line, what dimension does it have? Is it per the number of categories you have?
This one?
D.
Yeah. Okay. D has a category channel of category number. Yeah, because it's the category probability distribution.
Okay. What's the dimension? Does it have a spatial dimension?
Yeah. The spatial dimension, it has the same size of representation R.
Okay, and then the number of channel corresponds to the number of categories. Is that what you're saying?
Yeah.
Okay, all right. So channel then represents the probabilities of each of the class for each of the spatial elements. Yeah. Okay, is that how it goes?
It is achieved by.
Is that what the H prime operation does?
Yeah.
Okay, so how is that D? Oh, okay, do you define how D is calculated? How is it done?
It is achieved by one-by-one convolution. Actually, the difference between R and D is the channel. R has C channels and D has the category channels. Category number channel.
Okay, all right, okay. So you do the one-by-one convolution to the number of the categories you have. Okay.
Yeah, exactly.
Okay. So hopefully that it's trained to calculate the probability correctly here then.
Yeah.
Okay. All right. Thank you.
Thank you. And now we will get the R prime CK. Here CK represent, we total have K categories. And then now we will have, for every category, we will have a value, have a RCK prime corresponds to every category. And we will assign the above region representations to a matrix tensor according to the category label of corresponding element. And it is achieved by this formulation. And if the category probability equals to CK, and this region will be assigned with the same value. And I'm gonna show you an example. For example, for the category of card, we will assign a value for this region. And this just show a category. And finally, we will get a C channel matrix, and for every category regions, they will be assigned a corresponding value respectively. And this is the semantic level context module. And next, we will come to the loss function. The total loss function is the combination of LD and LO. For the first LD, it is calculated on the distribution D. It is the common cross entropy loss. And we first do the upsampling on the distribution D because the size of D is smaller than the original input. And then we will calculate the cross entropy loss. And for O, we get O from the representation RAUG. The RAUG equals to the concatenation of the R'(SL) and R'(IL), and the original representation R. This is the combination of these three representations. And we also do the upsampling for the RAUG. And then we will calculate the cross entropy loss. And for the hyperparameters for LD, in this paper, the author take the alpha equals to 0.4. And this is the overall loss function. Next, we will come to, yeah.
Can you go back? I'm kind of lost here. Okay. So D here,
yeah,
is really giving you class probability per each pixel, right?
Yeah, yeah, right.
And then you go down to the next slide, or stay here. And then you have on that line, the third bullet, D sub CK.
Yeah.
What's the difference between D sub CK and D?
We will get D CK from D. We calculate the DCK because we want to separate.
Oh, I see. Okay, your basic. So D sub CK is
category.
So D sub CK basically provides
for every category.
Basically what the likely what the category with high probability is, right?
Yeah,
That's
yeah,
what it's doing. And R sub CK, you're subjecting the same thing to R sub CK here.
Yeah, yeah.
What's the difference here? R sub CK is that representation you have, and you're taking that representation, argmax of that as C sub K, condition that is the case. How do you, I mean, D's and R's, okay, you, are they the same dimension though? Because R only has like what, they have different numbers of channels, right? D's and R's.
Yeah.
So, I don't know whether this is possible here. D sub star Rj and R sub star Rj. D's and R's don't have the same dimensions or the same number of channels.
R and D has the same, not same, different. They have the different channels. R have C channels and D have K channels.
Right. I'm trying to understand this equation here for R sub CK. For that argmax being C sub K. Okay, for that pixel, what does that do to R? I'm kind of confused here on this.
Oh, okay. I will introduce the N sub CK. It represents the number of representations belongs to category CK. And now, the author do these two operations is tries to separate the separate representation as the different regions or categories, so that he can, in the following, he can calculate the semantic level context information. So because during the training, the D prompt to get the right category probability predictions, so we can use the this to separate different categories and get the representations of R and the category probability distribution of D. For example, we assume that the CK represents the car, and we want to get the pixel representations of the car, and we, for example, here the CK represents 1 equals to car, and we will get the pixels which corresponds to the car in the representation, and we will get the R sub CK. And then we will.
Yeah, but R is, it's got multiple channels here, right?
Yeah, it has C channels. Yeah.
So you're assigning what are you? So okay, so R sub star. What does R sub star IJ have? Because you know D sub CK IJ, I get it, right? Because with the argmax, you know that particular pixel is for C sub K, right?
Yeah.
And so D sub CK has a value of the C sub K, right?
Yeah.
But on R sub CK, I have no idea what you assign here, because it says R star and IJ, right? What are you? What's the value of R sub CK?
We already know that I have C channels, and the shape is. Let's come back. The shape is this. It has C channels.
Okay.
And then for every category, we can get a RCK for every category, and C represents the channel. The NCK denotes the number of representations belongs to C, the category CK. NCK represents the number of representations belongs to one category for this category.
Okay, well, let's not get bogged down here. I may be the only one who don't follow this, so let's move on. Let's go to the next slide, please. Oh, okay. No, go back. Go back when you described about the loss here. So you compare the D sub K, H, and W, and K, well, this is the D that you got from the earlier slide.
Semantic-Level.
So
Yeah.
he has K, well, K stands for that category channels, right?
Yeah.
And then you compare that and compute the loss function with the ground truth.
Yeah.
How D accurately reflected the probability of the correct categories.
Yeah.
That
Exactly.
L sub D, I get that. Okay. But then on the O, where does O comes from? O sub star ij. Where does that come from?
O is the subsampling of the RAUG. RAUG is the concatenation of the representation.
So overall, that's the final output. Is that what it is? Okay.
Yeah.
Okay. And so that L sub D gets the loss function generated from only the semantic level context module.
Yeah.
And then the I guess this O is really the combined that comes from both ILCM and SLCM.
Yeah.
And hopefully this O sub star ij, that's really the final thing, right? That's the main thing that you want to come up with the correct answer as close to the ground truth.
Yeah.
But you're still adding L sub D for the loss as well. Okay. And okay, alpha's 0.4. So you actually have a way to reduce the influence of the L sub D. Okay.
Yeah.
Okay. All right. Thank you.
Thank you. Now let's come to the experiments. In this paper, the author tests the proposed methods on 4 different segmentation datasets. The first one is AD 20,000, and the second is Cocoa Staff, and then the LEAP, and finally the Cityscape. For the evaluation metrics, he adopts the most widely used mean intersection over union, MIOU, and he also compared the proposed method with the other methods with the flops, that is the floating point operations per second. And finally, evaluation metrics is the inference time. Let's come to the experiment results. And we can see that I will show you some ablation studies about the 2 different context module of this method. And the table 1 is the results when we only using the image level context module or semantic level context module, or both these two module. And the red line is the results. We can see that when we just use the baseline and the image level context module, there is a great improvement than the baseline. So actually, we can see that the image level contextual information is very important. And in the third row, we can see that when we just adopt the semantic level module, there also achieve good performance. And finally, when we adopt the 2 modules, there will be we will get the best results. We can see that the result indicates that the image level context module and the semantic level context module can complement and promote each other. So the result is the best. And here I will also show you the qualitative results when we just use the image level. I'll use the both image level and semantic level context module. We can see that the red column is the ground truth, and we can see that actually the red one here is also a picture. However, they are not showing the ground truth. but when we use the semantic level context module, it can capture the fine-grained details, so it can distinguish this part which belongs to the picture in this place, this region, and it can get the segmentation of this part. And by using the image level, we can see that the results have been improved. And the author also demonstrates the complexity comparison with existing context schemes. And we can see that no matter in the parameters of flops or the inference time, the proposed method will achieve fewer parameters and the fewer flops, and the inference time is also good. So,
okay, on this one, I'm kind of curious here because number parameters, when you only use ILCM or just SLCM, that's about 10 million, right?
Yeah.
But then when you use both, it only increased by 1 more million. When you actually look at the network, it seems you are really doubling the overall network complexity, and you only add 10% more. I don't follow that.
Let's go back.
So, you know, if you choose either ILCM or SLCM, your network is basically cut in half, right? Complexity wise. Or
actually,
at least at least 1/3, right? At least 1/3. Because you have R and then ILCM and SLCM. So, okay, those three. And then if you only use 2 of those, you know, you have 10 million a number of parameters. But when you use all 3, the number of parameters only increased by just 10%.
That's a question. Maybe I think I should check the code for the details.
Okay, and I'm also kind of suspicious about the flops here. You know, when you have both 180.6 gigaflops, so that's about, I don't know, compared to SLCM, that's about 15 more gigaflops. Yeah. But the time, the inference time is over 30 milliseconds more. Fraction-wise, that's a lot more. So am I missing something here? Shouldn't flops go linearly with the inference time? Maybe not. By looking at ILCM and SLCM, although flops higher for ILCM, inference time is less than SLCM. Yeah. So maybe there's some non-linearity here, how maybe flops are not really purely number of floating point operations here, right? Because by definition, flops mean how many computations you're computing. Yeah. Yeah. So I don't know how they came up with these numbers here. That seems a little suspicious. Okay. You can continue. Yeah. I think maybe there may be some more operations in the semantic level context information computation. So the inference time may be longer, maybe. Yeah, but then you said number of operations, but that's what flops mean, right? Yeah, so there are conflicts, I think. Yeah, let's go on. Okay. About the performance comparison here, this part is to further show the necessities of introducing the semantic level contextual information.
And we compare the performance of the proposed with the existing context schemes under the same training and testing sites. And we can see that the difference is that the compared methods, they all use the image level context schemes. However, in our proposed method, we also adopt the semantic level context information. So we can see that the proposed method is superior to the compared methods. And let's come to the experiment results when comparing with the state of the art. And the first one is the result on ADE 20,000 validation site. And we can see that even though when we use the ISNet 15, which is not stronger than 101, it can achieve some better performance than these first three methods. And when we adopt the ISNet 101, we will be better than the compared methods. And we can see that this is the results on this side. And for the COCO staff, the proposed method also achieved the comparative results. And we can see that the third is the dataset lib. This dataset is data different. It is a fine-grained semantic segmentation dataset, and it has additional challenges. For example, the complex close texture and the scale diversity of different categories, and the deformation of human body, and the fine-grained segmentation of the labels. So it is a very complex dataset. And we can see that the proposed methods, because this dataset is very complex, so the proposed method, the image level context module may be not very suitable for the tough dataset. So the author replaced the image level context module with the ASPP, and it also achieve comparative results. So it also it can also represent that the semantic level information is very crucial to improve the pixel representations. And finally is the cityscape dataset. We can see that the result further proves that the aggregating the image level and semantic level information can augment the pixel representation abilities. And finally, we will land on the conclusion. In this paper, the author tries to study the context aggregation problem. And the motivation is that he wants to overcome the existing image level context schemes. The problem is that too much contextual information of the other categories may lead to the misclassification. So he introduced the semantic level context information, and he introduced a image level context module and a semantic context module, so that he can aggregate the pixel representations with these two informations. And extensive experiments results have shown the effectiveness of the proposed method and the module. That's all my content for today's presentation. So is there any other questions?
Mr. Chin?
Yeah.
Mr. Chin.
예,
진영생 연구원. 참석했나?
네, 예, 있습니다.
질문 없나요?
질문은 딱히 없고 저도 그 지플롭이랑 타임 그거에 대해서 좀 궁금증을 갖고 있었는데 사실 명확하게 설명이 안 될 것 같아서 네, 따로 질문은 없습니다.
그럼 어쨌든 지금 참석했으니까 이
네.
문제는 지금 우리가 가지고 있는 장비로 이런 문제를 태클할 수 있나요? 여기 메모리라든지 이 number parameter 같은 걸 보더라도 가능합니까?
네네. 일단 제가 판단했을 때는 그 스피드가 너무 느려가지고 이 정도면은 1 fps 정도 나올 것 같거든요.
오케이. 네.
그리고 메모리는 잠시만 이거 그 메모리 사용량도 굉장히 많은 걸로 지금 확인이 되고 있습니다. 그래서 이 메소드보다 사실 좀 좋은 것도 많아가지고 사실 매력을 잘 못 느끼겠습니다.
네, 네. 더 이상 질문 없습니다. 수고하셨습니다. 재미있는
네.
논문이었습니다.
수고하셨습니다.
네,
Thank
수고했습니다.
you.
네.